Picture a single moment, an explosion so immense and powerful that it birthed everything: the stars, the planets, the very space and time we inhabit. That event, the Big Bang, was just the beginning of a story filled with cosmic drama, wonder, and transformation. From the fiery deaths of ancient stars to the silent, invisible forces shaping galaxies billions of light years away, the universe is a place of constant, breathtaking change. And in this video, we're going to explore 26 of the most extraordinary cosmic events that forever altered the fabric of reality. Each of these moments, whether a collision of neutron stars or the awakening of a supermassive black hole, reveals something profound about how our universe works and how it became what it is today. Think about the fact that the gold in your jewelry or the iron in your blood was forged in the heart of a dying star, then scattered across space in a cataclysmic supernova explosion. Or consider that the expansion of the universe is accelerating, driven by a mysterious force called dark energy, something we can't see or touch, yet it dictates the ultimate fate of everything. These aren't just abstract ideas, they're events that connect us directly to the cosmos. They shaped the world we live in, influenced the evolution of life, and continue to steer the future of the universe itself. We'll travel through time and space, from the first seconds after the Big Bang to the far future, where trillions of years from now, the last stars may flicker out. This journey isn't just about science, it's about awe. It's about standing face to face with the grandeur of existence and understanding our place within it. You'll witness how chaos gives birth to order, how destruction paves the way for creation, and how the universe constantly reinvents itself in the most spectacular ways. So settle in, open your mind, and get ready to explore the events that didn't just change the universe, they made it what it is, and they're still unfolding all around us, even now. 13.8 billion years ago, there was no space, no time, no matter as we understand it. There was only a single point of infinite density and temperature, a state scientists call a singularity. And then, in an event that defies all human intuition, this point began to expand, not into anything because there was no outside, but for the very first time, space itself began to stretch and grow. This wasn't an explosion in space, it was the explosive creation of space and time. In those first fleeting moments, the entire universe was smaller than a single atom, hotter than the core of any star, and it contained all the energy that would ever exist. From that unimaginable beginning, the cosmos as we know it started to take shape. This initial expansion forged the most basic building blocks of reality. The four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces separated from a single unified force, establishing the rules that would govern everything from the smallest particles to the largest galaxy clusters. Energy began to condense into the first subatomic particles like quarks and electrons, which would eventually form atoms. In less than a second, the universe underwent a transformation more profound than any other, setting in motion a chain of events that would lead to the formation of every star, every planet, and every living thing. It was the ultimate act of creation, a genesis written in the language of physics rather than myth. We know all of this not just through theory, but because we can still see the faint echo of that birth today. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. That primordial light is still all around us, permeating the entire cosmos as what we call the cosmic microwave background radiation. It's a fossil from the universe's infancy, and when astronomers map its tiny, whisper-quiet variations in temperature, they are essentially looking at a baby picture of the cosmos. These subtle fluctuations are the blueprints for the grand structures we see today, the seeds from which galaxies would eventually grow. Without that initial, violent expansion, the universe would be a cold, empty, and featureless void. The Big Bang gave us everything: the stage, the actors, and the physical laws for the entire cosmic drama that was about to unfold. But the story of the universe's beginning holds another, even more mind-bending chapter, one that happened in an almost impossibly brief instant. Right after the initial expansion began, the cosmos experienced something far more extreme, a growth spurt of unimaginable ferocity known as cosmic inflation. For a sliver of time so tiny it's almost meaningless to us, a fraction of a second so minute it makes a blink seem like an eternity, the universe didn't just expand, it exploded in size, doubling and redoubling its dimensions at a rate that defies comprehension. In less time than it takes light to cross a single atom, the entire observable universe was stretched from a speck smaller than a proton to something about the size of a marble. This wasn't a gentle unfolding, it was a violent, exponential stretching of the very fabric of spacetime itself. This incredible event solved some of the biggest puzzles left by the Big Bang. Look up at the night sky in any direction, and you'll see a universe that is remarkably smooth and uniform. The temperature of the cosmic microwave background radiation is almost exactly the same everywhere, a fact that was deeply confusing. How could regions of the universe now billions of light-years apart, regions that could never have been in contact with each other, have reached the same temperature? It would be like walking into a room where 1,000 people you've never met are all humming the same note in perfect pitch. Inflation explains this by suggesting that these distant regions were once intimately connected, nestled right next to each other before this period of ultra-rapid expansion blew them apart, locking in that uniformity. Yet, inflation didn't make the universe perfectly smooth. In fact, its most brilliant feat was leaving it just a little bit lumpy. At the quantum level, space is never still. It's a seething foam of virtual particles constantly flickering in and out of existence. Inflation grabbed these tiny, random quantum fluctuations and stretched them across the cosmos, magnifying them from microscopic quirks into macroscopic variations in density. These minute ripples in the fabric of the newborn universe became the gravitational seeds for everything that was to come. The slightly denser patches would, over billions of years, pull in more and more matter through gravity, eventually growing into the vast cosmic web of galaxies, clusters, and superclusters we observe today. Our Milky Way galaxy, and by extension our very existence, can be traced back to one of these infinitesimal quantum ripples, amplified to cosmic proportions during that frantic moment of inflation. Without this sudden, incredible burst of growth, the cosmos might have been a very different place, a chaotic, misshapen mess, or perhaps a cold, empty void without any structure at all. Cosmic inflation was the universe's crucial act of self-organization, a fleeting moment that set the precise initial conditions necessary for a rich and structured cosmos to evolve. It took a universe that was potentially unstable and sculpted it into one capable of giving birth to stars, planets, and life. This brief but monumental event handed the universe its blueprint, a template for grandeur written in the language of gravity and matter, setting the stage for the next critical step, the forging of the very first elements. With the universe now rapidly expanding and cooling from its initial unimaginable heat, a new and critical chapter began to unfold. In just the first 3 minutes after the Big Bang, the conditions were perfect for a grand act of cosmic alchemy. a process that would forge the very first atomic nuclei from the primordial soup of particles. This brief window, known as Big Bang Nucleosynthesis, was the universe's first and largest nuclear fusion reactor, operating on a scale we can scarcely comprehend. The entire cosmos was still incredibly hot and dense, a seething cauldron of protons and neutrons zipping around at tremendous speeds, constantly colliding with one another. It was within this frantic, high-energy environment that the simplest atomic bonds began to form, setting the initial chemical identity of everything that would ever exist. The sequence of events during these first few minutes was a delicate dance governed by precise physical laws. Initially, it was too hot for anything stable to form. Protons and neutrons would briefly stick together only to be immediately torn apart by the intense radiation. But as the universe expanded, its temperature plummeted. By the time it was about 1 second old, it had cooled enough for neutrons and protons to begin combining into the first atomic nuclei. The first and simplest combination was a deuterium nucleus, formed when one proton and one neutron managed to stick together. This deuterium then acted as a stepping stone, readily fusing with other particles to form helium. The process was incredibly efficient, with nearly all the available neutrons being quickly locked up into helium nuclei. In a cosmic blink of an eye, the universe went from a featureless plasma to one containing defined, albeit simple, atomic elements. The outcome of this frantic few minutes of fusion was a universe composed of about 75% hydrogen and 25% helium by mass, with only the tiniest trace amount of lithium. This is the primordial recipe, the base mixture from which every star, galaxy, and planet would eventually be built. What's truly remarkable is that the predictions scientists make about these ratios, based on our understanding of nuclear physics and the conditions of the early universe, match almost perfectly with the actual abundances we observe in the oldest regions of space. When astronomers look at ancient gas clouds or the atmospheres of very old stars, they find this exact 3-to-1 ratio of hydrogen to helium. This agreement between prediction and observation is one of the strongest pillars supporting the entire Big Bang theory. It's a successful forecast made about the composition of the entire cosmos based on events that lasted less than 3 minutes. The significance of this event cannot be overstated. Without Big Bang nucleosynthesis, the universe would be a profoundly boring and lifeless place. There would be no variety, no complexity, and no possibility for the future. Hydrogen and helium provided the fundamental fuel for the first stars. The gravitational collapse of vast clouds of this primordial gas is what ignited the fires of those first stellar giants, beginning the process of lighting up the cosmos. Furthermore, while these two light elements were essential, they were not sufficient for building planets or life. That would require heavier elements like carbon, nitrogen, and oxygen. But those could only be forged later in the hearts of stars and in their violent deaths. Nucleosynthesis provided the raw, base material, the blank canvas upon which stars would later paint with a much richer palette of elements. This initial act of creation set the stage for all the structure and complexity that was to follow, from the first glimmers of starlight to the evolution of life itself. For nearly 400,000 years, the universe remained a scorching, soupy fog, an impenetrable plasma where light was perpetually trapped. During this era, the cosmos was a chaotic mess of charged particles, free electrons, and naked atomic nuclei, all bouncing around in a dense, hot sea. Because these particles were electrically charged, they constantly interacted with photons, the particles of light. A photon couldn't travel more than a tiny distance before being scattered, absorbed, and re-emitted by an electron, effectively making the entire universe opaque. It was a constant, blinding, brilliant glow from every direction, but one that could not be seen through, like being stuck in the very center of the sun. This was the state of things for millennia, a lingering aftermath of the Big Bang's incredible heat. But the universe was expanding, and as it expanded, it was cooling relentlessly and inevitably. The temperature was dropping toward a critical threshold. That pivotal moment arrived when the universe was about 380,000 years old. The temperature had finally cooled to around 3,000 Kelvin, which is roughly half the temperature of the sun's surface. At this point, the energy of the raging photons was no longer powerful enough to keep electrons and protons apart. Suddenly and universally, a great cosmic marriage began. Negatively charged electrons were captured by positively charged atomic nuclei, primarily hydrogen and helium, forming the first stable neutral atoms. This process is what scientists call recombination, though the name is a bit of a misnomer, as the particles were combining for the very first time. It was a fundamental shift in the nature of the cosmos. The charged plasma that had filled space vanished, replaced by a gas of neutral, electrically inert atoms. The immediate and profound consequence of this shift was liberation. With free electrons now bound securely inside atoms, the roads were suddenly clear. Photons, which had been bouncing around helplessly for eons, were no longer being constantly scattered. They could finally stream freely across the universe. In an instant, cosmically speaking, the opaque fog lifted and the cosmos became transparent. That first flash of light, released from every point in space simultaneously, began its journey across the expanding universe. We detect that very light today, but it has been drastically transformed by its epic voyage. The expansion of space itself has stretched those once energetic photons, shifting them from visible light all the way down the electromagnetic spectrum into microwave radiation. This is the cosmic microwave background, or CMB, a faint, cold whisper of that first brilliant flash, now just about 2.7 degrees above absolute zero. This ancient light is arguably the most important discovery in all of cosmology. It is not coming from one place or one direction. It arrives at Earth from everywhere, a perfect, nearly uniform glow that fills the entire sky. It is the oldest fossil we can possibly observe, a baby picture of the universe when it was just a toddler. But this picture is not featureless. Incredibly precise instruments, like the Planck satellite, have mapped the CMB and found tiny, tiny variations in its temperature anisotropies. These minute fluctuations, differences of mere millionths of a degree, are the imprints of the density variations seeded by cosmic inflation. The slightly denser regions in this ancient map are the gravitational seeds that would, over hundreds of millions of years, pull in enough matter to form the first stars and galaxies. By studying these patterns, cosmologists can read the history and determine the composition of the entire universe, confirming the amounts of dark matter and dark energy with stunning precision. Recombination gave us a window directly into the infant cosmos, providing the hard evidence for our origin story. And with the fog of plasma finally cleared, the universe was, for the first time, dark and quiet, ready for the lights to come back on in a spectacular new way. After that brilliant flash of the cosmic microwave background faded into the expanding darkness, the universe entered a profound and silent chapter known as the Cosmic Dark Ages. For millions of years, space was a vast, black expanse filled only with the neutral hydrogen and helium gas forged after recombination. There were no sources of light, no stars to pierce the overwhelming blackness. It was a universe of pure potential, its fate resting entirely on the subtle gravitational seeds left behind from inflation. Those tiny, denser regions in the primordial gas were the only things that broke the perfect uniformity, and slowly, almost imperceptibly, gravity began to work on them. Over hundreds of millions of years, these pockets of slightly denser gas started to collapse under their own weight, pulling in more and more material from their surroundings. This was the long, quiet prelude to a cosmic dawn, the gathering of clouds that would eventually birth the very first fires in the cosmos. When these primordial gas clouds finally reached a critical density, the core of each collapsing sphere of hydrogen became so incredibly hot and pressurized that it triggered nuclear fusion. In a monumental flash, the first star was born. These pioneering stellar objects, known to astronomers as Population 3 stars, were unlike anything that exists in the modern universe. They were true behemoths composed exclusively of the pristine hydrogen and helium from the Big Bang, without any heavier elements to help radiate away heat during their formation. These clouds could collapse into absolutely massive structures. A typical Population 3 star might have been hundreds of times more massive than our Sun, and they burned at ferociously hot temperatures, shining with a brilliant, bluish-white light that was intensely rich in ultraviolet radiation. The ignition of these first stars was a revolutionary event that fundamentally changed the character of the cosmos. They brought an end to the Dark Ages, flooding the universe with light for the very first time since recombination. But their impact was far more profound than just illumination. Deep within their searingly hot cores, these stars became the universe's first true factories for creating heavier elements. Through the process of nuclear fusion, they began to smash hydrogen atoms together to form helium, and then, in their final life stages, they fused helium into carbon and oxygen. For the first time in history, the periodic table was growing more complex. However, these new elements were trapped inside the stars, unable to escape into the wider universe. That is, until the stars themselves reached the end of their spectacularly short lives. True to their immense size, these first stars lived fast and died young. A star hundreds of times the mass of our Sun consumes its nuclear fuel at a staggering rate. Where our Sun will shine steadily for billions of years, a Population 3 star might have blazed for only a few million years before succumbing to its own incredible power. Their deaths were not quiet affairs. They collapsed under their own gravity and then exploded in cataclysmic supernova of unimaginable force, far more energetic than any supernova occurring today. It was in these violent, final acts that the true legacy of the first stars was secured. Their explosions blasted the newly forged carbon, oxygen, and other elements out into the void, seeding the surrounding primordial gas with the first sprinkling of heavy atoms. This enriched gas would become the building material for the next generation of stars, stars that could be smaller, longer-lived, and could even be surrounded by rocky planets. The universe was no longer pristine. It was now on a path toward the complexity that would eventually make our existence possible. The lives of those first, monstrously massive stars were as brilliant as they were brief. Burning through their colossal reserves of hydrogen and helium fuel in just a few million years, a mere blink in cosmic time, they raced toward inevitable and spectacular ends. The final moments for a Population 3 star were a true spectacle of cosmic violence. Having fused elements all the way up to iron in their cores, these giants reached a point of no return. Iron fusion doesn't release energy, it consumes it, acting like a fire extinguisher at the star's very heart. With the outward pressure from fusion suddenly snuffed out, there was nothing left to fight the immense inward pull of gravity. In a fraction of a second, the core catastrophically collapsed, cramming a mass greater than our Sun into a sphere just a few dozen miles across. The rebound from this incredible implosion then triggered a shock wave of unimaginable power. blasting the star's outer layers into space at nearly the speed of light in a supernova explosion so energetic it would outshine an entire galaxy of modern stars. This wasn't just a brilliant flash in the early darkness, it was the universe's most crucial recycling program. For the first time, the heavy elements painstakingly forged in the star's core, carbon, oxygen, neon, silicon, and even iron, were not just created but liberated. The ferocious energy of the supernova, along with the extreme environments in its shockwaves, even managed to create elements heavier than iron, like gold, silver, and uranium, through a rapid process of neutron capture. All of these newly minted atoms were then hurled outward, enriching vast clouds of pristine hydrogen and helium with this first sprinkling of cosmic metals. This was the moment the periodic table truly began to diversify, moving beyond its two simplest ingredients. The interstellar medium, the raw material for all future stars, was no longer primordial. It was now seeded with the very stuff that would one day form rocks, oceans, and living organisms. The impact of these explosions rippled far beyond mere chemistry. The colossal energy released by each supernova sent powerful shock waves rippling through the surrounding gas clouds. These shockwaves acted like cosmic snowplows, compressing nearby nebulae and triggering them to collapse under their own gravity. In this way, the death of one population 3 star could directly initiate the birth of hundreds or even thousands of new second-generation stars. This created a feedback loop of creation and destruction. Star formation led to supernova, and supernova, in turn, prompted more star formation. This cycle began to sculpt the early universe, influencing how and where the first proto-galaxies would coalesce. The distribution of these heavy elements wasn't perfectly even. It created pockets of more enriched gas and voids that were still pristine, setting the stage for the diverse array of stellar populations and planetary systems we would eventually see. The legacy of these first supernova is quite literally all around us and even within us. Every atom of oxygen we breathe, every bit of carbon that forms the backbone of our DNA, and the iron that carries oxygen in our blood, all of it was forged in the heart of a long-dead star and scattered across the cosmos by a supernova explosion. Without these first monumental stellar deaths, the universe would have remained a simple, sterile soup of hydrogen and helium. There would be no rocky planets like Earth, no mineral diversity, and certainly no chemistry complex enough to give rise to life. These explosions were the necessary crucible, transforming the cosmos from a place of simple potential into one rich with the ingredients for complexity. This dissemination of newly forged elements didn't just fill space with stardust. It provided the fundamental building blocks that would allow gravity to begin its next great act of construction, pulling these enriched clouds into the first true galaxies. With a universe now seeded by the ashes of the first supernova, a new and more complex era of construction could begin. For hundreds of millions of years, the cosmos was a scattered collection of these second-generation stars and enriched gas clouds, all still drifting in the vast darkness. But the subtle gravitational seeds planted by inflation, and now amplified by the explosive deaths of massive stars, were about to bear their grandest fruit. Roughly 1 billion years after the Big Bang, gravity, the universe's great architect, began its most ambitious project yet. It started to gather these scattered stars and immense clouds of gas, along with its invisible partner, dark matter, pulling them together into the very first true galaxies. This was a monumental shift from a formless cosmic haze to a universe of defined structure, the birth of the first islands in the sea of space. These primordial galaxies were a far cry from the majestic spirals and smooth ellipticals we see today. They were tiny, fragile, and irregular things, often no larger than a tenth the size of our own Milky Way. Lacking the clear symmetry of modern galaxies, they likely resembled messy, clumpy globs of stars and gas. But what they lacked in size and order, they made up for in sheer activity. Within these first galactic nurseries, conditions were perfect for rampant star formation. The dense, turbulent clouds of gas, now enriched with heavy elements, could collapse efficiently into new stars. This made these early galaxies incredibly bright and energetic places, blazing with the light of countless young, hot stars. They were the universe's first stellar factories, working at a frantic pace to populate the cosmos with new suns. Crucially, these fledgling galaxies did not form in isolation. They were drawn together along invisible filaments of dark matter, the mysterious, invisible substance that makes up the majority of the universe's mass. This dark matter formed a vast cosmic scaffolding, a web-like structure across the expanding universe. The first galaxies began to light up at the intersections of these dark matter threads, tracing out the architecture of the cosmic web for the very first time. As they were pulled closer together by gravity, small groups of these dwarf galaxies began to merge. This was the next step in a hierarchical building process. Smaller structures coalesced to form larger ones. Through a slow, patient dance over billions of years, these initial mergers would create the majestic spiral galaxies and giant ellipticals that dominate the universe today. Our own Milky Way is a product of this ancient process, having grown to its current size by consuming countless smaller galactic building blocks throughout its long history. The formation of these first galaxies did more than just organize stars. It created complex ecosystems. Within the dense centers of these new structures, the first supermassive black holes found their homes, feasting on the abundant gas and growing to enormous sizes. The intense energy from these feeding black holes and the fierce radiation from countless new stars began to influence their environments in profound ways, heating surrounding gas and regulating further star formation. A galaxy became more than just a collection of stars. It was a dynamic, evolving entity, an engine of creation and change. The emergence of these cosmic cities fundamentally altered the narrative of the universe, setting the stage for the next acts of drama on an even grander scale. Deep within the hearts of those nascent galaxies, a sleeping giant was beginning to awaken. As vast rivers of gas and dust, enriched by the first supernova, flowed into the galactic centers, they fed the supermassive black holes that had likely been forming there since the earliest times. But now, these gravitational monsters found themselves at an all-you-can-eat cosmic buffet. As immense amounts of material spiraled inward, it didn't just fall straight in. It formed a seething, superheated disk around the black hole, spinning at nearly the speed of light. Friction within this whirling maelstrom of matter generated temperatures of millions of degrees, causing it to glow with a brilliance that defies imagination. This was the ignition of a quasar, the birth of the most persistently luminous objects in the entire universe. A single quasar, powered by a black hole weighing millions or even billions of times the mass of our Sun, can outshine every single star in its host galaxy combined. In fact, the light from one of these active galactic nuclei is so intense that it can be seen clear across the cosmos, billions of light years away. For perspective, if a quasar were placed at the distance of a nearby star like Sirius, it would appear brighter than our own Sun and would utterly sterilize Earth of all life. This incredible energy isn't just emitted as light. Quasars often fire off colossal jets of subatomic particles from their poles, shooting out across intergalactic space at nearly the speed of light for hundreds of thousands of light years. These jets act like cosmic blowtorches, carrying immense energy and depositing it far into the surrounding galactic environment. This wasn't just a spectacular light show. Quasars played a fundamental role in the evolution of the early universe. They became powerful regulatory engines. The intense radiation and energetic jets pouring out from a quasar would heat up the surrounding reservoirs of cold gas within its galaxy. Since stars form from cold, collapsing gas clouds, this heating effect effectively put a ceiling on star formation, preventing the galaxy from turning all of its fuel into stars too quickly. In some cases, quasars could even blow much of the galactic gas clean out into intergalactic space, starving the galaxy of future raw materials and effectively shutting down its growth. This process, known as quenching, helped determine why some galaxies became dead ellipticals early on, while others, like our Milky Way, had a more prolonged and gentle period of star formation. The supermassive black hole at the center, through its active quasar phase, was directly shaping the destiny of its entire host galaxy from the inside out. For astronomers today, these brilliant beacons are like cosmic lighthouses, their light having traveled for billions of years to reach us. By dissecting this ancient light with powerful telescopes, we can peer back to the universe's formative era, often called cosmic noon, when quasars were most common. We can study the conditions of the early intergalactic medium by observing how the quasar's light is absorbed as it passes through clouds of gas on its long journey to Earth. This allows us to take a core sample of the universe's history, layer by layer. The sheer existence of such bright quasars so early in the universe's history also presents a fascinating puzzle. How did these supermassive black holes have enough time to grow so enormous so quickly? Their presence challenges our models of black hole growth and continues to drive new theories about the origins of these gravitational giants. The era of quasars was a time of extreme cosmic energy, a period where the invisible engines at the center of galaxies revealed their power in the most dazzling way possible, setting the stage for the next great cosmic drama, the colossal collisions between the galaxies they called home. While the serene beauty of a spiral galaxy like our own Milky Way suggests a universe of tranquil order, the reality is far more chaotic and violent. Out in the deep reaches of space, a slow-motion ballet of destruction and creation is constantly underway, as galaxies are drawn together by their mutual gravitational pull in events that can last for billions of years. These are not the catastrophic, planet-shattering crashes one might imagine, but rather a profound and gradual intermingling, a cosmic dance where two vast collections of stars, gas, and dark matter merge to become something entirely new. This process of galactic collisions and mergers is not a rare catastrophe. It is a fundamental and frequent mechanism of growth and change, an engine of evolution that has shaped the universe we see today. When two galaxies begin their gravitational tango, their individual stars rarely, if ever, actually collide. The distances between them are so vast that they simply pass through one another like two swarms of bees merging. It is the immense clouds of gas and dust within each galaxy that truly feel the impact. As these clouds are violently compressed during the close encounters, they trigger massive, epic waves of new star formation, known as starbursts. Entire clusters of brilliant, blue, short-lived stars ignite in a fiery blaze of creation, lighting up the merging galaxies with incredible intensity. This is the universe's ultimate recycling program, where the raw material of old gas is forged into new generations of stars, often at a rate hundreds of times faster than in a quiet, isolated galaxy like our own. The final outcome of this billion-year dance depends on the size and type of the galaxies involved. When a large spiral galaxy consumes a much smaller dwarf galaxy, it's a process called galactic cannibalism. The larger galaxy may simply grow a little, its spiral arms becoming slightly distorted or thickened. But when two spiral galaxies of similar size merge, the result is a complete transformation. Their elegant disk structures are utterly destroyed in the gravitational turmoil, their stars thrown into new, random orbits. What emerges from the chaos is no longer a spiral, but a smooth, featureless, and football-shaped elliptical galaxy. This explains why the universe contains so many of these elliptical giants. They are the products of ancient mergers, the final fossils of colossal cosmic collisions. These events also have a dramatic effect on the supermassive black holes lurking at the galactic centers. As the galaxies merge, the black holes within them are drawn toward the new common center of gravity. They sink through the dense galactic core, eventually forming a binary pair that will orbit each other before finally merging themselves in an event that will shake the very fabric of space-time with gravitational waves. In the meantime, the merger funnels enormous amounts of fresh gas directly toward these black holes, feeding them and potentially igniting a brilliant quasar phase, turning the galactic center into a powerhouse that can influence the entire galaxy's future. This isn't just something that happens to others. Our own galactic home bears the scars of past mergers and is destined for a future one. The Milky Way's halo is littered with stellar streams and clusters, the shredded remnants of smaller galaxies it has consumed over billions of years. And in about 4.5 billion years, we are set for the main event, a slow-motion collision with our largest neighbor, the Andromeda Galaxy. Over millions of years, the two spiral giants will intertwine, their gravitational forces stretching and warping their structures, triggering a magnificent burst of new star formation before finally settling into a new, larger elliptical galaxy that some astronomers have nicknamed Milkomda. This event showcases the dynamic and ever-changing nature of the cosmos, where even the largest structures are not permanent, but are constantly evolving through interactions that are as destructive as they are creative. As individual galaxies and the groups they formed continued their gravitational dance on an ever grander scale, the universe began to assemble its most massive and impressive structures, galaxy clusters. Think of these not as simple gatherings of a few galaxies, but as true cosmic metropolises, vast cities in space where hundreds or even thousands of individual galaxies are all bound together by the relentless pull of gravity. These are not random assortments, they are the largest gravitationally bound structures known to exist, each one a colossal ecosystem where galaxies mingle like citizens in a bustling downtown, all immersed in a common atmosphere of incredibly hot, thin gas and surrounded by an immense halo of dark matter. The formation of a galaxy cluster is a slow, patient process dictated by the underlying architecture of the cosmos. It begins with the faint whisper of density fluctuations left over from the Big Bang, the same ones imprinted on the cosmic microwave background. Over billions of years, gravity amplifies these tiny ripples. Regions of space that were ever so slightly denser than their surroundings began to pull in more and more matter, first forming galaxies and galaxy groups, and then drawing these groups together into vast, sprawling assemblies. The most famous examples, like the Virgo cluster, which our own local group is slowly falling toward, or the immense Coma cluster containing over 1,000 galaxies, represent the end result of this process. They are the nodal points, the grand central stations in the vast cosmic web that structures the entire observable universe. Within these clusters, the space between the galaxies is far from empty. It is filled with a superheated plasma known as the intracluster medium, a gas so hot, reaching temperatures of tens of millions of degrees, that it shines brightly in X-ray light. This gas is a fascinating fossil record in itself. Its composition, enriched with iron and other heavy elements, tells the story of countless supernovae that exploded within the cluster's galaxies over eons, polluting the intergalactic environment with the ashes of dead stars. But perhaps the most critical role of galaxy clusters is their use as natural laboratories for studying the invisible. The sheer amount of gravity required to hold these fast-moving galaxies together is far greater than what the visible matter can account for. This was one of the first and strongest pieces of evidence for the existence of dark matter. By mapping how the cluster's gravity bends light from more distant objects, an effect called gravitational lensing, astronomers can essentially create a map of the cluster's total mass, revealing the massive, invisible dark matter halo that forms the true skeletal framework of the cluster. These clusters are not serene places. They are the sites of some of the most violent and energetic events since the Big Bang. When entire galaxy groups within a cluster collide with each other, the resulting release of energy is almost beyond comprehension. The most famous example is the Bullet Cluster, where a smaller group of galaxies has punched right through the center of a larger one. The collision was so violent that it actually stripped the hot gas from the two groups, leaving it lagging behind in a wake of shocked plasma. Meanwhile, the dark matter, which does not interact with anything but gravity, sailed right through the collision unscathed. This provided a stunning and direct proof of dark matter's existence, separating it from the normal, visible material. The study of such colossal collisions helps us understand how structure forms and how the different components of the universe, galaxies, gas, and dark matter behave under the most extreme conditions. This intricate organization of matter into a vast cosmic web, with clusters at its densest nodes, set the stage for astronomers to make an even more profound and unexpected discovery about the entire universe's fate. For centuries, the prevailing assumption in cosmology was a simple and seemingly intuitive one. The universe, born from the explosive force of the Big Bang, must be gradually slowing down. Every galaxy, star, and planet exerts a gravitational pull on every other. It stood to reason that this collective gravity, acting like a cosmic brake, would be relentlessly working against the initial momentum of the expansion, gradually decelerating the universe's growth. The only real question for astronomers was by how much. Would the pull of gravity be strong enough to one day halt the expansion entirely and reverse it in a cataclysmic big crunch, or would it simply slow it to a near standstill over trillions of years? This was the central dilemma, and in the late 1990s, two independent teams of scientists set out to measure this deceleration once and for all by using a very specific kind of stellar explosion as a cosmic yardstick. Their tool was the Type Ia supernova. These brilliant explosions occur in binary star systems when a white dwarf star steals enough material from its companion to exceed a critical mass limit, triggering a thermonuclear detonation that is remarkably consistent in its peak brightness. Because they all reach roughly the same intrinsic luminosity, astronomers can use them as standard candles. By measuring how bright these supernovae appear to us here on Earth, they can accurately calculate their distance. Furthermore, by analyzing the redshift of their light, how much it has been stretched to longer wavelengths by the expansion of the universe, they can determine how fast the universe was expanding at the time the light was emitted, billions of years ago. The plan was straightforward. Compare the expansion rate of the universe in the distant past to its rate today to quantify the deceleration. What they found, however, was not a slowdown. It was the opposite. The data from these incredibly distant supernovae revealed something astonishing and deeply counterintuitive. The stellar explosions were fainter, and therefore farther away, than their redshifts indicated they should have been if the universe had been expanding at a constant or decelerating rate. The only possible explanation was that the expansion of the universe was not slowing down at all. Instead, it was speeding up. Some mysterious, repulsive force was acting against gravity, pushing galaxies apart from one another at an ever-increasing rate. This discovery was so shocking that the researchers spent years painstakingly checking and rechecking their work, ruling out potential errors like intergalactic dust, dimming the light, or intrinsic variations in the supernova themselves. But the evidence was undeniable. In 1998, they announced their groundbreaking conclusion: the expansion of the universe is accelerating. The driving force behind this acceleration was given a name that reflected our profound ignorance of its nature: dark energy. This revelation sent shockwaves through the world of physics and astronomy, completely upending our understanding of cosmic evolution. It meant that the universe is dominated by something we cannot see, barely understand, and had not predicted. Follow-up measurements, particularly from the Planck satellite mapping the cosmic microwave background, have since precisely quantified the universe's budget. It appears that dark energy makes up about 68% of the total energy density of the cosmos. Ordinary matter, the stuff of stars, planets, and people, accounts for less than 5%. Dark matter, another mysterious component, makes up about 27%. This means that the force driving the ultimate fate of the entire cosmos is not the familiar pull of gravity from all the matter we can see and detect, but rather this enigmatic anti-gravitational pressure that we are only now beginning to grapple with. The nature of dark energy remains one of the greatest unsolved puzzles in all of science. The leading hypothesis is that it is a property of space itself, an energy inherent to the vacuum, often associated with Albert Einstein's cosmological constant, a term he famously inserted into his equations to achieve a static universe and later called his biggest blunder. It now appears he may have been right for the wrong reason. Alternatively, dark energy could be a dynamic field that changes over time, sometimes called quintessence. Or it could be a sign that our understanding of gravity, as described by Einstein's theory of general relativity, is incomplete on the largest cosmic scales. Whatever its true identity, dark energy's influence is absolute. It dictates the long-term destiny of everything. If it continues to accelerate the expansion as it is now, it will lead to a cold, isolated, and increasingly empty universe, a fate known as the heat death. If it strengthens over time, it could even tear apart galaxies, stars, and eventually the fabric of space-time itself in a catastrophic big rip. This profound discovery of an unseen force controlling our cosmic fate is inextricably linked to the search for another great unknown, a hidden component of mass that binds the universe together. While dark energy pushes the universe apart on the grandest scales, another, even more pervasive mystery holds it together from within. This invisible component, known as dark matter, forms the hidden skeleton of the cosmos, a vast, unseen framework upon which all visible structures are built. Its story begins not with a direct observation, but with a glaring discrepancy that astronomers simply could not ignore. In the 1930s, a brilliant and meticulous Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive gathering of over 1,000 galaxies. By measuring how fast these individual galaxies were whizzing around within the cluster, he could calculate the total gravitational pull needed to keep them all bound together, essentially, the cluster's total mass. He then compared this to the mass that was actually visible in the form of all the stars, gas, and dust he could see through his telescope. The numbers did not match. Not even close. The gravitational mass was hundreds of times greater than the luminous mass. The cluster should have flown apart long ago, yet it held together. Zwicky concluded that there must be a huge amount of some unseen, dunkel materie, or dark matter, providing the extra gravity. His idea was so radical that it was largely dismissed for decades. The case for this mysterious substance became undeniable in the 1970s with the work of astronomer Vera Rubin. She was meticulously mapping the rotation curves of spiral galaxies. That is, how fast stars orbit around the galactic center at different distances. According to the laws of gravity as we understand them, stars on the outer edges of a galaxy where visible matter becomes sparse should orbit much more slowly than those near the bright, dense center. Think of our solar system. Pluto, far out on the edge, moves much more sluggishly around the Sun than Mercury does close in. But what Rubin found in galaxy after galaxy was utterly different. Stars far out in the galactic suburbs were orbiting just as fast as those downtown. The only way this could be possible is if the entire galaxy, including its vast outer regions, was embedded within an enormous, massive halo of something invisible. This halo had to contain far more mass than all the stars and gas put together, its gravity gripping the outer stars and whipping them around at those unexpected speeds. This was the clincher. Dark matter was not just a curiosity in distant clusters, but an integral part of every single galaxy. But if we can't see it, how do we know it's really there? The answer lies in its gravitational signature, which it leaves everywhere. The most compelling modern evidence comes from a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. The immense gravity of a massive object like a galaxy cluster actually warps the fabric of spacetime around it, bending the path of light from more distant galaxies behind it. By measuring this distortion, astronomers can create a precise map of the cluster's total mass distribution. Time and again, these maps reveal that the bulk of the mass, the source of the incredible gravity causing the lensing, is completely invisible and does not align with the visible galaxies and hot gas. It forms a smooth, massive halo that permeates the entire cluster. This is a direct visual proof of dark matter's presence, separate from the normal stuff we can see. Furthermore, the detailed patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, are exquisitely sensitive to the amount of matter in the universe. The precise measurements from satellites like Planck tell us that dark matter must make up about 27% of the universe's total content, a number that fits perfectly with the observations from galaxy rotations and gravitational lensing. So what exactly is this stuff that makes up over 80% of all matter? That is the million-dollar question, or rather, the multi-billion-dollar question, as it has driven the construction of massive underground detectors and powerful particle colliders. The leading theoretical candidate is a class of particles known as WIMP, or weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and, as their name implies, interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. They would have been forged in the incredible heat of the Big Bang and now form a vast, diffuse sea through which our entire galaxy moves. Other candidates include actions, extremely light particles, or even primordial black holes, tiny black holes that might have formed in the first second of the universe's existence. Despite decades of searching, no experiment has yet definitively caught a dark matter particle, which only deepens the intrigue and pushes physicists to consider ever more exotic possibilities. The true legacy of dark matter is written across the entire cosmos. Without its immense gravitational scaffolding, the universe would look utterly different. In the early epochs, the gentle gravitational pull of dark matter's denser regions provided the initial seeds around which ordinary gas could accumulate. This gas could then cool, collapse, and eventually form the first stars and galaxies. The visible universe we see today, the brilliant spiral galaxies, the massive clusters, the vast cosmic web, is essentially just the traceable glitter sprinkled upon an invisible mountain of dark matter. It dictates the architecture of existence on the largest scales, guiding the formation of every structure we hold in awe. This hidden component is the silent, dominant partner in a cosmic dance, its gravitational embrace shaping everything from the path of a single star to the fate of the entire universe, all while remaining forever in the shadows. If the cosmic microwave background were a perfectly smooth, featureless wall of light, it would tell a profoundly boring story, a story of a universe born in perfect, sterile uniformity, with no potential for the rich structure we see today. But that is not what we see at all. When we look at this ancient light with instruments of incredible sensitivity, we find that it is not a uniform sheet. Instead, it is imprinted with a pattern of tiny temperature variations, a cosmic fingerprint of hot and cold spots that differ from each other by only about 1 part in 100,000. These minuscule fluctuations, known as anisotropies, are the single most important clue we have to understanding the origin and evolution of everything. They are the baby picture of the universe, and in their subtle patterns we can read the entire cosmic biography, from its first trillionth of a second to its ultimate fate. Unlocking this picture required a technological triumph, a series of space missions designed to map the entire sky with ever-increasing precision. It began with the Cosmic Background Explorer, or COBE, satellite in the early 1990s. COBE gave us our first blurry map of these anisotropies, confirming they existed and earning its researchers a Nobel Prize. This was followed by the Wilkinson Microwave Anisotropy Probe, WMAP, which provided a much sharper image, like going from a child's crayon drawing to a detailed photograph. Finally, the Planck satellite, launched by the European Space Agency, delivered the most exquisite, high-definition map of the early universe ever created, measuring these temperature differences with a precision that is almost unimaginable. These missions didn't just take a picture, they translated the faint whisper of the infant cosmos into a detailed data set that cosmologists could use to measure the fundamental parameters of the universe with astounding accuracy. So what created these all-important ripples in the first place? Their origin story takes us back to the very beginning, to a time of cosmic inflation. During that period of hyper-expansion, the universe was filled with a roiling sea of quantum fluctuations, tiny, random variations in energy that are a fundamental property of reality at the smallest scales. Inflation acted like a cosmic magnifying glass, stretching these subatomic quantum jitters across the entire sky, freezing them into place as slight differences in the density of matter and energy. These density variations are exactly what we see encoded in the hot and cold spots of the CMB. The slightly hotter regions correspond to areas that were a tiny bit denser in the early universe. The colder spots were ever so slightly more empty. It was in these over-dense regions that gravity got a head start, patiently pulling in more and more matter over hundreds of millions of years, eventually forming the vast cosmic web of galaxies, clusters, and superclusters that we see today. Every galaxy, including our own Milky Way, can trace its lineage back to one of these specific, slightly warmer patches on the CMB map. But the value of this cosmic fingerprint goes far beyond just explaining galaxy formation. By meticulously analyzing the precise size and distribution of these hot and cold spots, scientists have been able to perform what amounts to a cosmic blood test for the entire universe. The patterns tell us with remarkable precision that the universe is 13.8 billion years old. They confirm that ordinary matter, the atoms that make up stars, planets, and us, accounts for a mere 4.9% of the universe's total content. They tell us that dark matter makes up 26.8%, and that the mysterious force pushing the universe apart, dark energy, constitutes 68.3%. The CMB anisotropies have given us our standard model of cosmology, a recipe for the cosmos that is both incredibly precise and deeply humbling, revealing that the world we see is just a tiny fraction of what actually exists. This ancient light is our most direct connection to the universe's birth, a snapshot taken when it was just 380,000 years old. It is the foundation upon which our entire understanding of modern cosmology is built, providing irrefutable evidence for the Big Bang and painting a detailed picture of the universe's composition and geometry. It tells us the cosmos is flat, it tells us how fast it is expanding, and it sets the initial conditions for all the structure that would later evolve. This event wasn't just a moment in time. It was the moment the universe revealed its blueprints, offering us a clear window into its deepest secrets and setting the stage for the next era of cosmic drama, an era marked by explosions of almost incomprehensible violence. Just when we thought supernova represented the peak of cosmic violence, the universe unveiled an event so immensely powerful it defies all comparison: the gamma-ray burst. Imagine compressing the entire energy output of the Sun over its 10 billion-year lifetime into a blinding flash of light that lasts for less time than it takes to blink. These events are not merely explosions, they are the universe's ultimate death cries, beams of pure energy so intense they can briefly outshine every star in a million galaxies combined. For a few fleeting seconds, a single gamma-ray burst becomes the brightest source of light in the entire observable universe, a beacon of catastrophic energy visible clear across the cosmos. These incredible outbursts come in two distinct varieties, each with its own terrifying origin story. The longer bursts, lasting more than 2 seconds, are thought to be the birth screams of a new black hole. They occur when a truly massive star, dozens of times heavier than our Sun, completely exhausts its nuclear fuel. The core collapses instantly, not into a neutron star but directly into a black hole. As it does so, powerful jets of plasma are launched from its poles at over 99.99% the speed of light. If one of these ultra-relativistic jets is pointed directly at Earth, we see it as a long-duration gamma-ray burst, a brilliant, focused death beam announcing the creation of a new gravitational monster. The shorter bursts, lasting less than 2 seconds, have an equally dramatic source: the final, spiraling embrace of two neutron stars or a neutron star and a black hole. As these incredibly dense objects merge, they too can launch similar hyper-energetic jets for a brief instant, creating a short gamma-ray burst. What makes these events so valuable to science is not just their incredible power, but their incredible range. Because they are so phenomenally bright, they can be seen from the very edge of the observable universe, from galaxies so distant their light has been traveling to us for over 13 billion years. This makes them unparalleled probes of the early cosmos. When astronomers detect a gamma-ray burst from such a vast distance, they can use its light to study the conditions of the infant universe. As the burst's light travels through eons of space, it passes through clouds of gas and the halos of distant galaxies, absorbing specific wavelengths. By dissecting this light with powerful telescopes, scientists can conduct a core sample of cosmic history, analyzing the chemical composition and distribution of matter across billions of years. They serve as natural lighthouses, illuminating the dark stretches of space and time between galaxies, and helping us map the rate of star formation throughout cosmic history. There is also a sobering possibility that these distant events have directly touched our own world. Some scientists have proposed that a gamma-ray burst occurring within a few thousand light-years of Earth could have devastating consequences for life. The intense radiation from such a nearby burst would not cause immediate explosions or heat, but it would chemically alter our atmosphere. the high-energy photons would break apart nitrogen and oxygen molecules, leading to a series of reactions that destroy the planet's protective ozone layer. Without this shield, the sun's harmful ultraviolet radiation would pour down onto the surface, triggering a mass extinction event similar to the one that wiped out the dinosaurs. While the chances of a nearby burst are extremely low, geological evidence suggests it's a possibility that may have occurred in the distant past, a reminder that even events happening far across the galaxy can reach out with unexpected consequences. The study of gamma-ray bursts is a testament to our ability to decode the most extreme phenomena in the universe. From their initial detection by military satellites designed to monitor nuclear weapons tests to the rapid response networks of telescopes that now swing into action within seconds of a new burst detection, they represent a fascinating intersection of curiosity and cutting-edge technology. Each new detection peels back another layer of mystery, helping us understand the life cycles of the most massive stars, the physics of matter under the most extreme conditions imaginable, and the profound interconnectedness of cosmic events across space and time. They are the universe's most powerful and fleeting fireworks, a sudden, violent punctuation mark in the quiet narrative of cosmic evolution that demonstrates how creation and destruction are often two sides of the same coin. While the explosive deaths of massive stars are spectacular element forges, there is another, even more exotic cosmic event responsible for creating the very heaviest and most precious substances in the universe. This extraordinary process begins with the stellar remnants left behind by supernova, neutron stars. Imagine taking the mass of our entire sun and crushing it down into a sphere no larger than a city. The result is an object of almost incomprehensible density, where a single sugar cube-sized piece of material would weigh as much as a mountain. For billions of years, these cosmic diamonds can drift silently through the galaxy. But sometimes, two of them become gravitationally bound in a binary system, and their fate is sealed in a final, catastrophic dance. Locked in a tightening spiral, these two ultra-dense stars begin to lose energy in the form of gravitational waves, ripples in the very fabric of spacetime, as predicted by Einstein. This loss of energy causes their orbits to decay over eons, drawing them inexorably closer. In the final moments before collision, they whip around each other thousands of times per second, stretching and distorting each other with immense tidal forces until they finally smash together in a cataclysm of unbelievable violence. The merger is so energetic that it doesn't just create a flash of light, it shakes the universe itself, sending a powerful tremor through space-time that we can now detect here on Earth with observatories like LIGO and Virgo. The first time humanity ever witnessed this event was on August 17, 2017. Gravitational wave observatories detected the distinct chirp of two neutron stars merging, an event catalogued as GW 170817. For the first time in history, astronomers knew exactly where and when to point their telescopes. What they saw was a phenomenon entirely new to science, a kilonova. This is an explosion distinct from a supernova, powered by the radioactive decay of heavy elements blasted out from the merger. For about a week, this kilonova glowed with a peculiar, bluish light that then faded to red, a signature of complex atomic processes unfolding at an incredible rate. The true treasure of this event, however, was revealed in the light spectrum. The observed colors and lines were the unmistakable fingerprint of newly synthesized elements like gold, platinum, and uranium being created in real time. This was the definitive proof that neutron star mergers are the universe's primary smithies for these heavy elements. The intense neutron-rich environment during the collision, a process known as rapid neutron capture or the R process, is the only place with the right conditions to build these incredibly dense atomic nuclei. In that single event, astronomers estimated that an amount of gold many times the mass of our entire planet was forged and then blasted out into the surrounding space. The significance of this discovery cannot be overstated. It means that the gold in a wedding ring, the platinum in a catalytic converter, or the uranium used in nuclear power all originated from the spectacular collision of two dead stars that likely occurred billions of years before our solar system even formed. These events are rare, but over the history of the universe, they have seeded galaxies with the heavy elements necessary for the formation of rocky planets and the complex chemistry that underpins life itself. Beyond their role as cosmic jewelry makers, these mergers are also unparalleled natural laboratories. They allow us to test the laws of physics under the most extreme conditions imaginable, probing the nature of gravity itself and revealing the properties of matter at densities that cannot be recreated anywhere on Earth. This incredible alchemy, where the most destructive of events gives rise to the building blocks of technology and even life, finds a powerful parallel in the more common, yet equally vital, explosions of white dwarf stars. While the universe has many ways to create spectacular explosions, few are as precisely predictable or as cosmologically vital as the type Ia supernova. This particular kind of stellar death involves not the collapse of a massive star's core, but the complete and utter annihilation of a white dwarf, the Earth-sized ember left behind by a sun-like star. A white dwarf is a remarkable object, a sphere of degenerate matter where the inward crush of gravity is held at bay not by the heat of fusion, but by a quantum mechanical effect, the simple refusal of electrons to be squeezed any closer together. This state is stable, but it has a strict upper limit. If a white dwarf's mass is pushed beyond about 1.4 times that of our Sun, a threshold known as the Chandrasekhar limit, this delicate balance shatters catastrophically. The path to this disaster is almost always a galactic partnership gone wrong. Most white dwarfs exist in binary systems, orbiting a companion star. If the two stars are close enough, the intense gravity of the white dwarf can begin to siphon material, primarily hydrogen, from its partner. This stolen gas accumulates on the white dwarf's surface, building up pressure and heat until it ignites in a series of gentle, periodic nova outbursts that blow off some of the outer layers. But if the accretion rate is just right, the white dwarf can steadily and quietly gain mass over millions of years. As it inches closer to that critical 1.4 solar mass limit, the core experiences unimaginable pressures and temperatures. Suddenly, the carbon that makes up the bulk of the white dwarf can no longer resist. In a fraction of a second, carbon fusion ignites not in a controlled burn, but in a runaway thermonuclear inferno that rips through the entire star from the inside out. There is no remnant, no neutron star or black hole left behind. The entire white dwarf is utterly vaporized in an explosion so uniform and so powerful that it can briefly outshine an entire galaxy. This incredible consistency is what makes Type Ia supernova the gold standard for cosmic cartography, because every single one is triggered by the same physical mechanism. A white dwarf reaching the same critical mass limit, they all explode with nearly the same intrinsic peak brightness. This makes them what astronomers call standard candles, perhaps the most important ones ever discovered. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with incredible accuracy. It's like knowing the exact wattage of a light bulb. By seeing how faint it looks, you can tell exactly how far away it is. By finding these supernovae in distant galaxies and measuring their apparent brightness, astronomers can accurately gauge vast intergalactic distances, building a precise ladder that reaches across the cosmos. This property is what allowed two teams of researchers in the late 1990s to make the most shocking cosmological discovery of the last century: that the expansion of the universe is not slowing down due to gravity, as everyone had assumed, but is instead accelerating, driven by a mysterious force now called dark energy. They used the reliable, standardized light of distant type Ia supernova as their mile markers. By looking at supernova billions of light years away, they were looking back in time, measuring how fast the universe was expanding in its youth. To their astonishment, the distant supernova were fainter than expected, meaning they were farther away than their redshift indicated they should have been if cosmic expansion were slowing. The only possible explanation was that space itself had begun stretching faster over time, pushing galaxies apart at an ever-increasing rate. This discovery, which earned the Nobel Prize in Physics in 2011, completely overturned our understanding of the universe's fate and its fundamental composition. Beyond their role as cosmic tape measures, these explosions are also prolific distributors of the elements that make rocky worlds like our own possible. The intense nuclear furnace of the explosion forges a vast amount of iron, along with silicon, nickel, and other intermediate mass elements. In a single event, a Type Ia supernova can blast an entire solar mass of newly minted iron out into the interstellar medium. This iron will eventually mix with other gas clouds and become incorporated into future generations of stars and planets. The very iron core of our own planet Earth, and the iron that courses through our blood, owes its existence to these specific kinds of stellar explosions that occurred long before our solar system was born. They are a crucial link in the cosmic cycle of element creation and distribution, ensuring that the ashes of dead stars are recycled into new worlds with the potential for life. While the thermonuclear detonation of a white dwarf is a precise and predictable event, the death of a truly massive star is a far more chaotic and violent spectacle. These stellar giants, born with more than 8 times the mass of our Sun, live fast and die young, but their final act is one of the most important recycling processes in the cosmos. Their journey ends not with a quiet fade, but in a cataclysmic core collapse supernova, an explosion so powerful it can, for a brief moment, outshine its entire host galaxy. This isn't just a brilliant light show, it is the primary mechanism by which the universe distributes the heavy elements essential for planets, and ultimately for life itself. The road to this spectacular demise is paved by the star's own internal fusion factory. For millions of years, it has been fusing progressively heavier elements in its core, much like a layered onion. Hydrogen fuses into helium, helium into carbon, and so on, all the way up to iron. But here, the process hits a wall. Fusing iron into heavier elements doesn't release energy, it consumes it. Suddenly, the star's core, which has been supported for its entire life by the outward pressure from fusion, loses its central support system, with no energy being generated to fight the immense inward crush of gravity. The core collapses catastrophically. In less than a second, an iron core the size of Earth is compressed into a ball of neutrons barely 10 miles across. The collapse doesn't end quietly. The outer layers of the star, now with nothing underneath them, come crashing down at nearly a quarter the speed of light. They hit the newly formed, incredibly dense neutron core and rebound in a titanic shockwave that blasts the entire star apart. This explosion does more than just tear the star to pieces. It creates the conditions for one last act of cosmic alchemy. The incredible flood of neutrons in the expanding shockwave allows for the rapid neutron capture process, forging elements heavier than iron, like silver, gold, and uranium, in a matter of seconds. Meanwhile, the intense heat of the explosion fuses lighter elements, creating vast quantities of oxygen, carbon, neon, and calcium. In this single, violent event, the star returns its enriched contents to the galactic environment, seeding future generations of stars and planets with the raw materials for complexity. The energy released is almost beyond comprehension. For a few weeks, the supernova can emit as much energy as our Sun will over its entire 10 billion-year lifetime. But the light we see is only a tiny fraction of the total energy. The vast majority is carried away by ghostly particles called neutrinos, which flood out of the collapsing core in an unimaginable torrent. In 1987, when a star went supernova in the Large Magellanic Cloud, a galaxy neighboring our Milky Way, detectors on Earth picked up a handful of these neutrinos a full 3 hours before the light from the explosion arrived. This detection from supernova 1987 was a landmark event, confirming our models of core collapse and opening the new field of neutrino astronomy. The aftermath of such an explosion is just as important as the event itself. The expanding shock wave from the supernova slams into the surrounding interstellar medium, compressing gas and dust and triggering the formation of new stars. The most famous example is the Crab Nebula, the beautiful tangled remnant of a supernova observed by Chinese astronomers in 1054. Inside that nebula lies a pulsar, a rapidly spinning neutron star that is the dense corpse of the original star's core. These stellar remnants, along with black holes formed from the most massive collapses, are the final products of these giant stars. They are the universe's way of ensuring that even in death, there is creation, scattering the elements of life across the galaxy and setting the stage for the next act of cosmic construction. All across the galaxy, in the glowing cradles of young stars, the universe begins its most delicate work of construction. The violent deaths of massive stars and the mergers of neutron stars have enriched vast clouds of gas and dust with a rich palette of heavy elements: silicon, iron, carbon, oxygen, and more. When such a cloud collapses to form a new star, it doesn't all fall directly into the stellar furnace. Conservation of angular momentum, a fundamental law of physics, ensures that much of this material instead forms a spinning, flattened disk around the infant sun, a cosmic whirlpool of potential known as a protoplanetary disk. Within this swirling maelstrom of gas and rock and ice, the chaotic and beautiful process of building planets begins. This is the era of accretion, a word that simply means growth by gradual accumulation. It starts with the smallest of steps: microscopic dust grains of silicon and carbon inherited from long-dead stars begin to stick together through electrostatic forces, a process charmingly called dust sticking. These tiny clumps grow into pebbles, then into rocks, and then into kilometer-sized bodies called planetesimals. At this scale, gravity takes over as the primary architect. These planetesimals attract one another, colliding and merging in a series of events that range from gentle mergers to violent, moon-shattering impacts. Over millions of years, this chaotic dance of collision and assimilation results in the formation of planetary embryos and finally, full-fledged planets. The composition of these new worlds is dictated entirely by their location within the disk. Close to the heat of the young star, only rock and metal can condense, leading to the formation of dense terrestrial planets like Earth. Further out, beyond the frost line, ices can also solidify, allowing for the rapid growth of massive planetary cores that then go on to attract enormous envelopes of hydrogen and helium gas, becoming gas giants like Jupiter and Saturn. Our own solar system is a perfect and deeply personal example of this process in action. Roughly 4.6 billion years ago, a modest cloud of gas and dust, enriched by generations of supernova, began to collapse. At its center, our sun ignited. Around it, the material in the disk began to coalesce, with countless collisions building the worlds we know today. The inner solar system saw the formation of 4 rocky planets: Mercury, Venus, Earth, and Mars. The asteroid belt between Mars and Jupiter represents the leftovers from this construction zone, planetesimals that never managed to form a planet due to the gravitational influence of the growing Jupiter. Further out, the gas giants Jupiter and Saturn formed, while the ice giants Uranus and Neptune took shape in the colder, darker reaches. Beyond them, a vast reservoir of icy planetesimals was left behind, a region we now call the Kuiper Belt. This entire, intricate architecture emerged from that simple, spinning disk. For centuries, we could only wonder if other stars had similar families of planets. Today, thanks to missions like NASA's Kepler Space Telescope, we know the answer is a resounding yes. The discovery of exoplanets has revealed that planet formation is not the exception, but the rule. Most stars in our galaxy are now believed to host at least one planet, and many have complex systems that rival or even dwarf our own in scale. We have found a staggering diversity of worlds: hot Jupiters orbiting blisteringly close to their stars, super-Earth rocky planets larger than our own, and even planets orbiting in the habitable zones of their stars, where temperatures might be just right for liquid water to exist on the surface. This ubiquity transforms our perspective. It suggests that the basic ingredients and processes that led to our solar system are common cosmic occurrences, a natural and frequent outcome of star formation. The profound implication of this 18th cosmic event is the bridge it builds between the grand, impersonal forces of the universe and the intimate possibility of life. The iron in Earth's core, the silicon in its rocks, the carbon that forms the basis of our biology, and the water in our oceans, all of it was delivered to the protoplanetary disk that formed our sun and planets by the spectacular deaths of earlier stars. The formation of planetary systems is the ultimate act of cosmic recycling, where the ashes of stellar explosions are gathered up and reassembled into new worlds. It creates localized, stable environments where the complex chemistry of life can potentially begin. The universe, through the simple, mechanical process of accretion, creates countless protected niches where the laws of physics and chemistry can play out in novel ways. Yet, for all its creative power, the cosmos also possesses a destructive capacity, a reminder that the very process of building planets also leaves behind debris that can threaten them. The serene, clockwork regularity of our solar system's planets orbiting the Sun belies a hidden history of incredible violence, a past punctuated by random and catastrophic collisions. While the process of planetary formation was itself a story of countless smaller impacts, the era of planet building never truly ended. It simply transitioned into a new phase where the leftover debris of the solar system, the asteroids and comets, became agents of both destruction and delivery. These wandering remnants, often called planetesimals, are the ghosts of the solar system's formation, and their occasional intersections with planets have written pivotal chapters in the history of every world, including our own. On airless worlds like the Moon and Mercury, this violent history is preserved in perfect detail, their surfaces a pockmarked testament to a period known as the Late Heavy Bombardment, which occurred around 4 billion years ago. But even today, the solar system is a dynamic shooting gallery. Jupiter, with its immense gravity, acts as a cosmic vacuum cleaner, frequently drawing in comets that might otherwise threaten the inner planets. The spectacular impact of comet Shoemaker-Levy 9 into Jupiter in 1994 was a stark reminder that these events are not just ancient history. The comet, torn into a string of fragments by Jupiter's gravity, slammed into the planet's southern hemisphere with the force of millions of nuclear weapons, leaving dark scars in the cloud tops that persisted for months. It was a dramatic show of how planetary landscapes are continually being shaped by external forces. For Earth, however, the role of impacts has been far more profound than just crater formation. There is a compelling theory known as panspermia, which suggests that the very ingredients for life may have been delivered to our planet by comets and asteroids. These icy or rocky bodies are known to be rich in organic molecules, the complex carbon-based compounds that serve as the building blocks of life. Analyses of certain meteorites that have fallen to Earth have revealed the presence of amino acids and nucleobases, the fundamental components of proteins and DNA. It is entirely plausible that during the early, fiery bombardment of our planet, a constant rain of these cosmic projectiles seeded the young Earth's oceans with this primordial organic soup, providing the raw materials that would eventually, under the right conditions, jump-start the chemistry of life. In this view, we may all be descendants of stardust not just in a metaphorical sense, but in a very literal one, our biological lineage tracing back to molecules that arrived on rocks from outer space. Yet, for all their creative potential, these impacts also wield an unimaginable destructive power, capable of resetting the entire course of evolution in a single, terrible moment. The most famous and pivotal example is the Chicxulub impact event, which occurred 66 million years ago. An asteroid or comet perhaps 6 miles wide, traveling at hypersonic speed, slammed into what is now the Yucatan Peninsula in Mexico. The energy released was equivalent to billions of atomic bombs, instantly excavating a crater over 100 miles wide and launching billions of tons of vaporized rock and superheated ejecta high into the atmosphere. The immediate effects were apocalyptic. Searing heat pulses ignited global wildfires, and colossal tsunamis thousands of feet high scoured coastlines across the globe. But the true killer was the long-term environmental collapse. The ejected material, along with soot from the fires, circled the globe, blotting out the sun for months or even years. Photosynthesis ground to a halt, collapsing the base of the food web. Acid rain poisoned the oceans and continents. This dramatic change in climate and environment led to the Cretaceous-Paleogene extinction event, which wiped out an estimated 75% of all plant and animal species on Earth, most famously the non-avian dinosaurs. This catastrophic clearing of the ecological stage was, however, a moment of opportunity. With the dominant dinosaurs gone, small, surviving mammals were able to emerge from the shadows, diversify, and eventually rise to become the new dominant land animals. This impact, therefore, was not merely an end. It was a new beginning that directly paved the way for the age of mammals and ultimately the rise of humans. The cosmos, in its random and violent way, had a direct hand in shaping the biological destiny of our planet, a reminder that our existence is contingent upon a long and fragile chain of cosmic events. This monumental event, known as the Giant Impact Hypothesis, paints a picture of our early solar system that is far more violent and dynamic than the serene arrangement of planets we see today. Imagine the scene. Earth, still a molten, partially formed planet, is cruising through a chaotic young solar system littered with planetary embryos and debris. Then from the void comes Theia, a protoplanet roughly the size of Mars on a catastrophic collision course. This was not a simple sideswipe or a glancing blow. It was a direct, head-on impact of almost unimaginable force. Theia slammed into the early Earth, and in that single, shattering moment, the destiny of our world was forever altered. the energy released was so immense that it effectively melted the entire planet for a second time, vaporizing a significant portion of Earth's mantle and the entirety of the impactor itself. This wasn't just a crash, it was a merger of two worlds, a cosmic forge of incredible violence that would give birth to our most familiar celestial companion. The evidence for this cataclysmic origin story is written in the very rocks of the Moon and the fundamental dynamics of our planet. Perhaps the most compelling clue lies in the composition of the Moon itself. Samples brought back by the Apollo missions revealed that the Moon is surprisingly similar to Earth's mantle in its isotopic fingerprints, the specific ratios of different atomic variants of elements like oxygen and titanium. If the Moon had formed elsewhere and been captured by Earth's gravity, its composition would likely be very different. The giant impact model elegantly explains this similarity. The Moon formed primarily from the mantle material of both Earth and Theia that was blasted into orbit by the impact, while the dense metallic cores of the two bodies coalesced at the center of the new, larger Earth. This also explains why the Moon has such a small iron core relative to its size. Furthermore, the event provides a perfect explanation for Earth's tilted axis, which gives us our seasons, and for the angular momentum of the Earth-Moon system, the speed of Earth's rotation and the Moon's orbit. The physics of the impact imparted a specific spin, setting the initial conditions that have evolved over billions of years to what we observe today. The immediate aftermath of the impact was a world transformed into a vision of hell. Earth was now encircled by a torus of superheated vaporized rock, a glowing ring of debris that quickly coalesced under its own gravity to form the proto-moon. This new satellite would have been much closer to Earth initially, appearing as a terrifyingly large, red-hot orb dominating the sky. Its gravitational pull would have generated tides thousands of times more powerful than those we experience now, sloshing the planet's still molten surface and contributing to a global magma ocean. For millions of years, the system settled, with the Moon steadily migrating outward due to tidal interactions, a process that continues at a rate of about 1.5 inches per year. This gradual retreat has been slowing Earth's rotation over eons, lengthening our days from just a few hours to the 24 we know now. The long-term consequences of this violent birth are what truly make it a pivotal cosmic event for life. The Moon acts as a gravitational stabilizer for Earth's axial tilt. Without its steadying influence, our planet's tilt would wobble chaotically over time, much like Mars does. This would lead to wildly unpredictable and extreme climate variations, making the stable, long-term environmental conditions necessary for the evolution of complex life nearly impossible. The Moon's gravity is also responsible for the tides, which have played a crucial role in the history of life on Earth. The rhythmic pulsing of the intertidal zone is thought to have been a nursery for early life, encouraging species to adapt to both aquatic and terrestrial environments and potentially driving the migration of life from the oceans onto the land. Beyond the biological, the presence of a large, bright moon in the night sky has undoubtedly influenced the cultural and intellectual development of humanity, inspiring mythology, art, early timekeeping through lunar calendars, and serving as a constant beacon for curiosity and exploration. The story of the Moon's formation is a powerful testament to a recurring theme in cosmic history: chaos and destruction giving rise to order and opportunity. A random, devastating collision between two embryonic planets, an event of pure catastrophe, ultimately created the precise conditions that allowed our stable, life-bearing world to exist. It gave us the steady climate, the rhythmic tides, and the celestial timepiece that have all been silent partners in the story of life on Earth. This event reminds us that our place in the universe is not a product of serene, isolated evolution, but rather the result of a long and violent history of cosmic accidents and grand constructions, where even the most destructive forces can sculpt the foundations for a living world. For a long time, our picture of the solar system was a beautifully simple, almost static one. A star formed in the center of a swirling disk, and the planets that coalesced from that disk simply settled into the orbits where they were born, a permanent and unchanging family portrait. But this serene image is a cosmic illusion. We now understand that planetary systems are dynamic, chaotic, and often violent places in their youth, where entire worlds can embark on vast journeys, migrating inward or outward from their birthplaces due to complex gravitational interactions. This grand reshuffling, known as planetary migration, is not a rare event. It appears to be a fundamental and common process in the construction of planetary systems, and it has profoundly shaped the architecture of our own cosmic backyard. The most dramatic story of migration in our solar system likely involves the king of the planets, Jupiter. According to a leading model called the Grand Tack hypothesis, Jupiter's early history was anything but regally stable. After forming much further out, perhaps beyond the current orbit of Neptune, the young gas giant began a slow inward march. Its immense gravity plowed through the primordial disk of gas and dust, clearing a path as it spiraled closer to the Sun. This inward journey might have brought Jupiter as far in as the orbit of present-day Mars, putting it perilously close to the inner, rocky planet-forming region. This single movement would have had catastrophic consequences for anything trying to form in its path, scattering protoplanetary material and starving the area of building blocks. This could elegantly explain a long-standing puzzle: why Mars is so surprisingly small, a mere tenth the mass of Earth, when models predicted it should be a larger world. But Jupiter's journey did not end with it plunging into the Sun. Just in time, a gravitational balancing act is thought to have occurred. As Jupiter migrated inward, its smaller sibling, Saturn, was also forming and beginning its own inward migration. Eventually, the two gas giants became locked in a specific orbital resonance, a kind of gravitational synchrony where their orbital periods matched up in a simple ratio. This resonance created a powerful, combined gravitational pull on the gas disk itself. The tide turned. The combined gravity of Jupiter and Saturn began to push back against the forces dragging them inward, halting their deadly march and reversing it. The two giants then began a coordinated outward migration, with Jupiter settling into its current orbit and Saturn following suit. This gravitational tack, much like a sailboat changing direction, saved the inner solar system from being completely devoured and allowed the material that would become Mercury, Venus, Earth, and Mars to finally coalesce in a now cleared out zone. This ancient gravitational dance left behind fingerprints that we can still observe today. The asteroid belt, that vast collection of rocky debris between Mars and Jupiter, is a direct relic of this migration. It is not the remains of a shattered planet, but rather a region that was never able to form one because of Jupiter's gravitational influence. The Grand Tack model explains the belt's strange mix of compositions. Jupiter's inward journey would have scattered dry, rocky asteroids from the inner solar system out into the belt, while its outward journey dragged water-rich, icy bodies in from the outer solar system, creating the diverse population we see now. Furthermore, the existence of so-called hot Jupiters in other star systems, gas giants orbiting incredibly close to their stars, provides direct observational evidence that migration is a common process. These behemoths could not have formed where they are now. The intense heat and lack of material so close to a star make it impossible. They must have formed further out and then migrated inward, a journey that, unlike Jupiter's, did not have a Saturn to pull them back from the brink. This realization that planets can move fundamentally changes our understanding of how habitable worlds come to be. A planet forming in the Goldilocks zone, where conditions are just right for liquid water, is no guarantee of a life-bearing world. A migrating gas giant could easily fling such a promising planet out into the cold darkness of interstellar space, or send it careening into its parent star. Conversely, migration could also deliver vital ingredients for life from the cold outer reaches to the inner system, much as Jupiter may have done by delivering water-rich material to the early Earth. The dynamic history of our solar system, with its grand gravitational rearrangements, highlights that planetary systems are not static sculptures but evolving narratives, where the final arrangement of worlds is the product of billions of years of gravitational interactions, near misses, and cosmic billiards. This understanding of our solar system's dynamic youth naturally leads us to consider the ultimate source of stability that made it all possible: the long, steady burn of the Sun itself. While the dynamic dance of planets and the violent collisions of asteroids have shaped our solar system's architecture, none of it would matter without the steady, life-giving presence at its center. For 4.6 billion years, our Sun has been the unwavering anchor of this cosmic neighborhood, a beacon of stability in an otherwise chaotic universe. This remarkable period of constancy, known as its main sequence lifetime, is the reason you and I are here today. It represents a golden age of equilibrium, a delicate balancing act where the immense inward crush of gravity is perfectly countered by the outward pressure generated by nuclear fusion in its core. Deep within the Sun's heart, a continuous and staggering process unfolds. Every second, 600 million tons of hydrogen are fused into 595.9 million tons of helium. The missing 4.1 million tons of mass are converted directly into energy, as per Einstein's famous equation, flooding the solar system with the light and heat that powers every leaf, every ocean current, and every weather system on Earth. This isn't a frantic, explosive process but a controlled and steady burn, the hallmark of a main sequence star. The Sun's sheer size creates a natural gravitational pressure cooker, maintaining the core at a temperature of about 15 million degrees Celsius and a density 10 times that of lead. Under these extreme conditions, protons, the nuclei of hydrogen atoms, can overcome their mutual electrical repulsion and get close enough for the strong nuclear force to take over, welding them together into helium. This energy then begins a long journey outward. It bounces around inside the Sun for tens of thousands of years, absorbed and re-emitted countless times by the dense plasma, until it finally reaches the surface and radiates into space as the sunlight we recognize. This incredible engine has been running with remarkable consistency, its output varying by less than 0.1% over human history, providing a stable environmental platform upon which the entire saga of life on Earth has been able to unfold. Consider the profound implications of this stability. It took billions of years for the first single-celled organisms to evolve into the complex, multicellular life we see today. That evolutionary journey required a climate stable enough to allow for gradual adaptation, not one subject to wild, star-induced swings in temperature and radiation. The Sun's steady output allowed Earth's climate system to find a balance, enabling water to remain liquid on the surface for eons. This constancy allowed photosynthesis to evolve and become the foundation of the planetary food web. It allowed atmospheres to develop and stabilize, and it provided the reliable daily cycle of light and darkness that governs the biological rhythms of almost every creature on the planet. In a very real sense, the predictable nature of our parent star is the single greatest reason Earth is a living world. It is the cornerstone of our habitability, the silent partner in every chapter of biological history. Studying the Sun, therefore, is about much more than understanding our own star. It is the key to unlocking the life cycles of the hundreds of billions of other stars that fill our galaxy. By meticulously observing sunspots, solar flares, and the subtle oscillations on its surface, a field of science called heliosismology, we can peer into the Sun's interior structure, much like geologists use earthquakes to understand Earth's core. This detailed knowledge provides the foundational model against which we compare all other stars, allowing us to accurately gauge their ages, compositions, and future fates. Our Sun serves as the essential Rosetta Stone for stellar astrophysics, a nearby laboratory where we can test our theories about how stars are born, live, and die. Its well-understood main sequence phase gives us the confidence to predict that in about 5 billion years, this long period of stability will finally come to an end, setting the stage for a dramatic and ultimate transformation that will redefine our entire solar system. For billions of years, the Sun has been the steadfast anchor of our solar system, a reliable furnace burning hydrogen in its core with a consistency that has allowed life to flourish on Earth. But this stability is not eternal. It is merely a phase in the life of a star, and that phase will one day come to a spectacular and definitive end. In about 5 billion years, the Sun will have consumed nearly all the hydrogen fuel in its core. The delicate balance that has defined its main sequence life, the outward pressure of fusion fighting the inward crush of gravity, will begin to falter. With a fusion engine sputtering, gravity will gain the upper hand, causing the core to contract and heat up even further. This collapse, however, will not be the end. Instead, it will ignite a new, more volatile chapter, triggering a series of transformations that will utterly dismantle the solar system we know. The first act of this final drama will be the Sun's expansion into a red giant. As the core contracts, the incredible heat generated will push the Sun's outer layers outward with immense force. The star will begin to swell, its surface cooling and turning an ominous red hue as it grows. It will engulf the orbits of Mercury and Venus without hesitation, vaporizing both worlds into nothing more than a memory. The real question mark hangs over the fate of our own planet. While Earth's orbit might technically place it just at the edge of the expanding Sun's atmosphere, it is unlikely to survive. Even if it isn't completely consumed, the intense heat from the nearby stellar surface will scorch our world, boiling away the oceans and melting the very rock of the crust, leaving behind a barren, glowing cinder. The Sun will dominate the sky, a bloated, red orb that stretches from horizon to horizon, a terrifying and beautiful sight for any hypothetical observer left to see it. This giant phase is turbulent and relatively brief. The Sun will become unstable, pulsating and shedding its outer layers in a series of violent convulsions. These expelled layers of gas will not simply vanish. They will form a vast, intricate cloud of incandescent gas and dust around the dying star, a planetary nebula that will glow fiercely under the intense ultraviolet radiation from the exposed hot core. For tens of thousands of years, this nebula will be a brief but brilliant monument to the Sun's death, a cosmic work of art visible from distant star systems. Meanwhile, all that will remain of the Sun's former glory is its core, now exposed and lacking the pressure for further fusion. This incredibly dense, Earth-sized ember, known as a white dwarf, will be intensely hot initially, but with no energy source left, it will slowly, over trillions of years, cool and fade away into a cold, dark stellar remnant. The death of the Sun is a profound reminder of the impermanence of all things. even the seemingly permanent celestial bodies that anchor our existence. It marks the definitive end of our solar system as a living, dynamic family of planets. Yet, in the grand, cyclical narrative of the cosmos, this ending is also a beginning. The material ejected during the red giant and planetary nebula phases, enriched with heavier elements like carbon, oxygen, and nitrogen that were forged in the Sun's final stages, will be blown back into the interstellar medium. There, this stardust will mix with other cosmic debris, eventually becoming part of a new generation of molecular clouds. These clouds are the nurseries for future stars and planets, meaning the atoms that once made up the Earth, the planets, and even our own bodies could one day be incorporated into new worlds, perhaps even ones that orbit new stars and host new life. The Sun's death is not just an annihilation. It is a vital act of cosmic recycling, a poignant link between the end of one story and the beginning of countless others, forcing us to widen our gaze from the fate of our star to the ultimate destiny of the entire universe. But this grand cosmic cycle of star birth and death, of galaxies merging and planets forming, cannot continue forever. The universe has an expiration date, and its fate is written not in fire or ice, but in a slow, inexorable slide into absolute stillness. Based on our current understanding of physics and the relentless acceleration driven by dark energy, the most likely final chapter for everything is a state known as the heat death of the universe. This is not a dramatic explosion or a violent collapse, but rather the ultimate triumph of entropy, the natural tendency of all systems to move from order to disorder. Imagine a cup of hot coffee left alone in a room. It doesn't stay hot. Instead, its heat spreads out, dissipating into the surrounding air until everything reaches the same lukewarm temperature. The entire cosmos is undergoing this same process on an unimaginable scale, a gradual and irreversible evening out of all energy. The timeline for this event is so vast it defies human comprehension. We are talking about timescales measured not in billions, but in trillions upon trillions of years. The first act of this long farewell will be the end of starlight. Over the next 100 billion years or so, the last reserves of interstellar gas will be exhausted, and the formation of new stars will cease entirely. The existing stars will, one by one, burn through their fuel. Some will end as white dwarfs, others as neutron stars or black holes, but all will eventually cool and fade. The universe, once ablaze with the light of 100 billion galaxies, will grow dim. The brilliant pinpricks of light that have defined the cosmic landscape will wink out, leaving behind a dark sea of stellar remnants and failed stars known as brown dwarfs. The darkness, however, is just the beginning. Over even more staggering timescales, the very structures of matter itself may begin to unravel. Some speculative theories suggest that the protons which form the core of every atom might not be perfectly stable, but could actually decay over periods exceeding a decillion years. That's a 1 followed by 33 zeros. If this proton decay is real, then even the cold, dead cinders of stars and planets would not be permanent. Every physical object, from a rogue asteroid to a black dwarf, would very slowly but surely evaporate into a faint mist of subatomic particles and radiation, further contributing to the featureless, lukewarm soup of the universe. The final players in this cosmic endgame are the black holes, the most resilient structures in the universe, but even they are not immortal. Through a quantum mechanical process at their boundaries called Hawking radiation, black holes slowly leak energy and lose mass. For a stellar mass black hole, this evaporation process takes an almost unimaginable length of time, but for the supermassive giants at the centers of galaxies, it takes longer still. Eventually, after timescales so long that they make the current age of the universe seem like a single blink, even the last black hole will emit its final, faint whisper of radiation and vanish from existence. At this point, the universe will reach its final state. There will be no stars, no planets, no atoms, and no recognizable structures. The cosmos will be an incredibly vast, nearly perfect vacuum, filled only with an ultra-dilute sea of photons and fundamental particles, all at the same infinitesimally low temperature. With all energy evenly distributed, no heat can flow from one place to another, no work can be done. Every chemical reaction, every biological process, every motion of any kind will become impossible. The universe will be, for all intents and purposes, dead, frozen in a state of maximum entropy. While this vision of the far future is profoundly bleak from a human perspective, it serves a powerful purpose in the here and now. It drives our deepest scientific curiosity, the quest to understand dark energy, the nature of time, and the fundamental laws of thermodynamics is, in many ways, a race to see if this fate is truly inevitable or if other, more exotic possibilities exist. It forces us to confront the ultimate transience of all things, from the mightiest galaxy to the most fleeting thought, and in doing so, it imbues our present moment with a breathtaking and precious fragility. The universe may be headed for an eternal silence, but right now, it is still singing a brilliant and complex song, and we are here to listen. While the heat death presents a slow, cold fade into nothingness, there exists a far more dramatic and violent alternative for the cosmos's final act, one that hinges entirely on the enigmatic behavior of dark energy itself. This scenario, known as the Big Rip, trades the universe's gradual sigh for a final, terrifying scream. It all depends on a specific property of dark energy called its equation of state, essentially a measure of its pressure and density. If this value crosses a certain critical threshold, indicating that dark energy's repulsive force grows stronger over time and, crucially, strengthens as the universe expands, then the fate of everything changes from a slow freeze to a sudden and absolute shredding. The acceleration we observe today would not just continue, it would exponentially increase, becoming an unstoppable force that doesn't just push things apart, but actively tears the very fabric of reality at its seams. The timeline for this apocalypse is staggering, even by cosmic standards. Current models suggest this catastrophic unraveling could begin in earnest roughly 22 billion years from now. The end would not come all at once, but in a horrifying sequence of destruction that would systematically dismantle the universe from the largest scales down to the smallest. The first casualties would be the largest structures, as the expansion rate becomes more violent than the gravitational glue holding them together. Galaxy clusters would be the first to be pulled apart. Galaxies within them would be flung into the ever-expanding void, their shapes distorted and then dissolved. Next, the galaxies themselves would be ripped asunder. The gravitational bonds holding individual stars together would be overcome, sending each star flying off on its own lonely trajectory into the accelerating darkness. But the horror would only be beginning. As the expansion rate continues to intensify, it would eventually turn its attention to the stars and planets themselves. The force binding a star together, the immense gravity created by its own mass, would be no match for the cosmic repulsion tearing at it from all sides. First, planets would be stripped away from their parent stars. Then, the stars would be vaporized, their constituent gas clouds violently dispersed. In the final moments, the expansion would become so ferociously powerful that it would target the very building blocks of matter. The gravitational and nuclear forces that hold atoms together, the fundamental bonds that constitute reality as we understand it would be overcome. In a final, fleeting instant, every molecule, every atom, every proton and electron would be torn apart from one another, rendered into a universe of disconnected, fundamental particles unable to ever interact again. Space-time itself, the stage upon which the cosmic drama has played out for billions of years, would be shattered beyond repair, leaving behind a meaningless, featureless void where the concept of distance or connection has lost all meaning. The Big Rip Scenario is more than just a speculative doomsday. It is a powerful thought experiment that highlights the profound mystery at the heart of modern cosmology. We call the force behind this dark energy, but that is merely a placeholder for our ignorance. Its true nature remains one of the greatest unsolved puzzles in physics. Is it a constant force woven into the vacuum of space itself as Einstein's cosmological constant? Or is it something dynamic and evolving, a field that could change in strength over time, perhaps even a fifth fundamental force of nature we have yet to properly describe? The possibility of a big rip forces physicists to consider these alternative theories and to design ever more precise observations to measure the evolution of dark energy's strength across cosmic history. Every new telescope and sky survey brings us closer to understanding whether this terrifying fate is our ultimate destiny, reminding us that the universe's story is still being written, and its final paragraph could be one of unimaginable violence. But what if our entire universe, with all its galaxies, stars, and laws of physics, is not the entirety of existence? What if it is merely one bubble in a vast, frothing cosmic sea, one page in an infinite book of realities? This is the staggering proposition of the multiverse concept, an idea that pushes the boundaries of cosmology from the study of a single cosmos to the potential of a meta-universe containing countless others, each with its own unique properties and perhaps even its own fundamental laws of nature. This isn't merely science fiction. It arises as a natural, though still speculative, consequence of our most successful theories about the very beginning of everything, particularly the theory of cosmic inflation. The same mechanism that explains the uniformity and structure of our universe may also imply that the process of inflationary expansion did not happen just once, but is in fact eternal, continually spawning new pocket universes in an unending creative cascade. The driving force behind this radical idea is a profound puzzle known as the fine-tuning problem. When we examine the fundamental constants of our universe, the strength of gravity, the mass of an electron, the precise value of the cosmological constant, we find that these numbers seem exquisitely, almost miraculously, calibrated to allow for the existence of complex structures and life. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. If the nuclear forces were different, stars would be unable to forge carbon and oxygen, the essential elements for life as we know it. The odds of all these constants aligning by random chance in a single universe are astronomically low. The multiverse offers a compelling, if mind-bending, solution to this riddle. If there are an infinite number of universes, each with randomly dialed physical constants, then it is no surprise that we find ourselves in one of the rare habitable ones. We are not a lucky accident. We are a statistical inevitability in a vast ensemble where every possible configuration of physics is realized somewhere. This concept finds a strong foothold in the leading theory of our own universe's birth, eternal inflation. The idea is that the inflationary energy that blew up our universe is not a one-time event, but a pervasive field that can decay in some regions like ours, to form a stable, hot Big Bang universe while continuing to expand exponentially in the spaces between. In those still inflating regions, quantum fluctuations can spawn new bubbles of decay, which themselves become self-contained universes, forever disconnected from our own. Each of these bubble universes could undergo its own version of recombination, star formation, and evolution, but potentially with completely different physical laws. In one universe, gravity might be repulsive. In another, there might be 4 fundamental forces instead of 3. The possibilities are literally endless, a cosmic landscape of unimaginable diversity where the laws of physics we hold as universal constants are merely the local bylaws of our particular cosmic neighborhood. Of course, this remains one of the most speculative frontiers of science. By its very nature, the existence of other universes outside our observable spacetime is profoundly difficult, if not impossible, to test directly with current technology. Critics rightly point out that a theory that predicts everything potentially explains nothing, and that the multiverse concept risks moving beyond the realm of testable science into the domain of metaphysics. However, scientists are incredibly creative, and they are exploring potential indirect signatures. Some have looked for evidence of a collision between our universe and another bubble universe in the patterns of the cosmic microwave background, a kind of cosmic bruise on the edge of our observable reality. Others are investigating the deep mathematical structures of string theory, which naturally predicts a colossal number of possible vacuum states, each corresponding to a different set of physical laws that could be realized in different pocket universes. Regardless of its current testability, the multiverse idea represents a monumental shift in perspective, a Copernican revolution on the grandest possible scale. It challenges our deepest assumptions about uniqueness and causality, suggesting that our universe's story is not the only story, but one narrative in an infinite library. It forces us to confront the possibility that all that we see, all that we are, is the product of a much vaster, more complex, and perhaps even impersonal meta-reality. This doesn't diminish our universe's wonders. Instead, it expands our sense of awe to encompass the breathtaking potential of all that might exist beyond the horizon of our perception, forever redefining what it means to be a part of the cosmos. Looking back across this immense cosmic timeline, from the initial singularity to the speculative edges of the multiverse, a profound pattern emerges, one that transcends any single event to reveal the fundamental character of the cosmos itself. The universe is not a static museum exhibit. It is a dynamic, evolving, and deeply interconnected system where creation and destruction are not opposites, but partners in an endless dance. The most breathtaking acts of Genesis are almost always born from moments of incredible violence. A massive star must die in a supernova, scattering its enriched guts across light years to provide the raw materials for rocky planets and the chemistry of life. 2 galaxies must collide and tear each other apart to trigger the birth of millions of new stars and give rise to an entirely new galactic structure. Even our own moon, a symbol of constancy and romance, is the product of a catastrophic planetary collision that forever altered Earth's destiny. This theme of creation from destruction is the universe's most powerful engine of change, a cycle of death and rebirth written into the fabric of physical law. This cycle is governed by a delicate and constant interplay between chaos and order. The initial conditions of the Big Bang were almost perfectly smooth, a canvas of near uniformity. Yet, it was the microscopic chaos of quantum fluctuations, those random, seething energy shifts at the smallest possible scale, that were amplified by inflation to become the seeds of all future structure. Chaos provided the raw variation, gravity then provided the ordering principle, patiently pulling those slight density variations into galaxies, stars, and planets over billions of years. We see this same dance everywhere, in the chaotic turbulence of a protoplanetary disk that gives rise to the precise orbits of planets, in the violent, chaotic core of a supernova that forges and distributes elements with incredible precision. The universe seems to use chaos as a tool, not as an obstacle, to build ever more complex and ordered systems. It is a process that doesn't seek a final, static peace, but rather a sustained, dynamic equilibrium where change is the only constant. Perhaps the most humbling realization is the profound interconnectedness of it all. Each event we've explored is not an isolated incident but a crucial link in a chain of causality that spans billions of years. The precise ratio of hydrogen to helium forged in the first 3 minutes set the stage for the first stars. The deaths of those stars filled the cosmos with the carbon, oxygen, and iron that would later form our Earth and our very bodies. The gravitational pull of dark matter sculpted the cosmic web that guided the formation of galaxies, within which stars and planets could reside. This tapestry of cause and effect means that we are literally made of stardust, our existence directly tied to events that occurred in distant galaxies and long-vanished stars. The iron in our blood, the calcium in our bones, and the oxygen we breathe are all souvenirs from a cosmic journey that began at the dawn of time. Understanding these grand themes does more than satisfy scientific curiosity. It reshapes our perspective on our place in the cosmos. It fosters a deep sense of humility, reminding us that our planet, our species, and our moment in history are infinitesimally small within a story 13.8 billion years in the making. Yet it also inspires a powerful sense of wonder and curiosity. The same physical laws that govern the spin of a galaxy also dictate the orbit of an electron. The same processes that build stars also shape the weather patterns on our world. We are not separate from the universe. We are an active, conscious part of its ongoing evolution, capable of looking back and unraveling the very story that led to our existence. This cosmic perspective invites us to see ourselves not as passive inhabitants, but as participants in a grand, unfolding narrative, one that is still being written across the vast expanse of space and time. And so, our journey through the cosmos comes to a close, a voyage that has stretched from the very first fraction of a second to the trillions of years that may lie ahead. We've witnessed the universe not as a static backdrop, but as a living, breathing entity in a state of constant, breathtaking flux. From the singular spark of the Big Bang to the silent, cold whisper of heat death, every event we've explored is a vital thread in an immense and intricate tapestry, each one setting the stage for the next in an unbroken chain of cause and effect that defines reality itself. This narrative tells us that we are not merely observers of this cosmic drama. We are active participants, woven into the story by the very atoms that make us who we are. Think about that for a moment. The calcium that strengthens your bones was forged in the heart of a massive star that died long before our sun was born. The oxygen you breathe with every breath was released in the violent death throes of that same star, scattered across light years to eventually become part of the cloud that gave rise to our solar system. The gold in a wedding ring or the uranium in a power plant originated from a cataclysmic collision between two ultra-dense stellar corpses. We are, quite literally, the universe made conscious, a way for the cosmos to look back upon itself and contemplate its own origins, its own majesty, and its own uncertain future. This connection is the most profound takeaway, a truth that binds our existence to the grandest scales of space and time. This exploration does more than just fill us with wonder. It underscores the relentless, humble curiosity that drives us forward as a species. Every discovery we've discussed, from the nature of the cosmic microwave background to the accelerating expansion driven by dark energy, is a testament to human ingenuity. It represents centuries of collective effort, of building upon the work of those who came before, of designing ever more powerful tools to peer deeper into the void and ask the next great question. The story of the universe is also the story of our quest to understand it, a saga of expanding horizons that shows no sign of slowing down. There are always new mysteries to solve, new frontiers to push, reminding us that the pursuit of knowledge is one of our most noble and defining endeavors. As we turn our gaze back to our own world, this cosmic perspective offers a powerful sense of context. It highlights the incredible fragility and rarity of our planet, a pale blue dot suspended in a sunbeam, teeming with life against unimaginable odds. It reminds us that the divisions we create are inconsequentially small when viewed against the backdrop of a galaxy that contains hundreds of billions of stars and a universe that contains hundreds of billions of galaxies. The challenges we face, while immense to us, are set against a canvas of cosmic time and space that can inspire both humility and a renewed sense of shared purpose to protect our unique and precious home. The greatest lesson woven through these 26 events is that change is the only true constant in the universe. Stars are born, they live, and they die. Galaxies collide and merge. The very fabric of space itself is stretching and evolving. This impermanence is not something to fear, but a fundamental source of the universe's creativity and beauty. It is the engine that has driven the progression from a universe of pure energy to one filled with galaxies, planets, and life. It means that the story is far from over. New chapters are being written every second, in the heart of every star, in the swirl of every galaxy, and in the endless expansion of the dark between them. The universe's story is still being written, and in a very real way we are helping to write it. Thank you for joining me on this incredible journey. I'd love to hear which of these cosmic events resonated most with you in the comments below. If you enjoyed this deep dive into the mysteries of space, be sure to subscribe and hit the bell so you don't miss our next adventure. Until then, keep looking